So this is homework 17. So again, I'm going to quickly go through some of these questions so that you kind of have some feedback. So this first question, choose a statement that's not true. So this first one says the equation for calculating chi-squared is the same for goodness of fit and test of independence. That is true. Values for chi-squared could be negative, positive, or 0. That is not true. Chi-squared, because we're basically just adding the difference, squaring it, dividing by whatever. Anyway, it's only ever going to be positive. It cannot be negative, and it could be 0 if the expected values were exactly the same as the observed values in every single category. But anyway, it could technically be 0, but it can't be negative. The shape of the chi-squared distribution depends on degrees of freedom. That is technically true. It's always going to be kind of that skewed right shape that I've kind of talked about. But how tall that first part is, or how soon that first part kind of happens, and then how quickly it drops off, all of that kind of depends on degrees of freedom. So technically, yes, the shape of the distribution depends on degrees of freedom. And then the chi-square test should only be performed on categorical data. That is true. We're dealing with categorical data. If we had numerical data, we would do like a 2-sample t-test or a 1-sample t-test or whatever that we've learned before. So scenario 1, major snack food company claims that its chips are America's favorite. Statistics class tests this claim by asking a sample of 90 random students to select their favorite chip, brand A or 2 other brands. Below are the results of how many students are selected. Our distribution model would be this 33%, 0.3% for all 3 categories. The reason is kind of our null would be that people like the chips equally. And what this major snack food company is trying to prove is that it's not equally distributed, and in fact that their brand has a higher percentage. So it's a little bit tricky. Chances are, if they don't give you this is a goodness of fit test, if they don't give you specific percentages for each category, it's probably going to be one where we divide it equally. So 100% divided by 3 categories would be 33.3. So then fill in the missing components. So expected values, we would take the 90 random students and divide them equally. So 33.3% of 90, or just 90 divided by 3, however you want to do that, should be 30. So my expected count for each one is going to be 30. Degrees of freedom is just categories minus 1. So we have 3 categories. 3 minus 1 is 2. And then the chi-squared critical value, again, it comes from your chi-squared table. And they said 0.05 on this one, and my degrees of freedom is 2, so 5.99 would be my critical value. And then the chi-squared statistic. My expected counts are all 30, and then those are my observed. So I'm going to use my calculator to set this up the way I showed you guys. And now I'm using L3 to calculate my chi-squared statistic the way I've showed you. And now I'm going to add them together the way I've showed you. So my statistic, my chi-square statistic is 3.46 repeating, and they want 2 decimal places, so we would round that to 3.47. So what conclusion? Based on this, and I'm going to always draw it out because that's how my brain works. So I have my kind of chi-squared model that's going to be skewed right. My critical value is 5.99, so anything past 5.99 would be considered in the critical region. And my chi-squared statistic was 3.47, so not quite there. I'm having trouble writing today. So it is not in the critical region, so we would fail to reject, which basically means we don't have evidence that there's a major difference from what we expected. And again, what we expected up here was an equal in each brand. So we do not have evidence to say that there's a difference from that. Basically, we don't have evidence to say that Americans overall, on a grand scheme, prefer brand A to the other brands. We saw in the numbers that brand A was higher. What we're saying with this is that it's not significantly higher. It's not significantly different from these expected values of 30, 30, 30. The second scenario wants to know is there an association between marital status and the color of car that you drive. So we have now 2 variables, whether you're married or unmarried, and what color your car is. So this would be a chi-square test of independence. Another clue there is if they're asking about association between variables, that's a good clue that it's a test of independence as well. But again, you're looking for, do we have 1 variable or 2? The null hypothesis would basically be that marital status is unrelated to your color of your car, or that there is no relationship between them, there's no association, they're independent. So that would be this one, car color is independent of marital status. It has nothing to do with it, that your marital status does not impact at all the color of your car. How would you calculate the expected number of married people that drove red cars? So married people that drove red cars would be this top left column. And remember, expected count is row total times column total divided by grand total. So for this one, first thing you would want to do is figure out what your totals are. So I'm going to do that real quick. So I've done that. So again, my expected count for the times column total is 80 divided by grand total is 150. Should be that one. Degrees of freedom for a test of independence. Your degrees of freedom is the number of columns minus 1. Sorry, I had trouble there. Times the number of rows minus 1. So we have 3 columns, so 3 minus 1 is 2, and then we have 2 rows, 2 minus 1 is 1, 2 times 1 is 2. Another trick I kind of mentioned in class once is that if we kind of cover up one of the rows and cover up one of the columns, however many cells you have left is your degrees of freedom. So that's another way of looking at it. And all of that, when you're determining degrees of freedom on a test of independence, we are not counting the total row and column. We're only counting the actual data. So that's why I didn't even look at those numbers. So 2 is my degrees of freedom. Critical value, again, comes from the table. So again, 0.05 unless they tell you a different alpha. And then for 5.99, I think that was the same as the last one. 2 degrees of freedom is popular, apparently. And then we want the chi-squared statistic. So for that, we're going to have to find all of our expected counts and then put them in the tables the way I've shown you before. We're using the same formula for chi-squared. So what I'm going to do on this one, just so I can have everything in one spot, is I'm going to make a new table just for my expected counts so that I have them on the screen. And then I'm going to go in my calculator and do the chi-squared math. So those would be my expected counts. So then to find my chi-squared actual statistics, I'm using that same formula that I did for the goodness of fit test. And I can use the same method in my calculator as I did for the goodness of fit test. I just have to pay attention to the order I put the observed so I can make sure I do the expected in the same order. And I'm just going to type over these numbers that are there from the last one. So now I'm using L3 to find the chi-squared statistic like always. And then I'm going to go second quit and add together L3. So my chi-squared statistic is 1.766, 3 decimal places, so that is perfect. All right. One thing I will say on this one, it didn't actually specify at any point what to round our expected numbers to. I just did 1 decimal place. So if you had rounded them to 2 decimal places, you might have gotten a slightly different answer for your chi-squared statistic, but always pay attention if they tell you at any point to round your expected counts to a certain number of decimal places. Make sure you do that because that could affect your answer for your chi-squared statistic. Okay, I'm coming back later. My 1.766 was counted wrong on this one. So again, what I was just saying is that I rounded my expected counts to 1 decimal place. This particular question did not specify at any point what I should round them to. It will on the test or on the problem set. So make sure you pay attention to that. But if you were following along and you typed in something similar and got it wrong, that is probably why. It's because you rounded to a lower number of decimal places. So, it accepted answers between 1.75 and 1.76. So again, I'm guessing it has to do with the rounding of the expected counts. So on this one, my critical value is 5.99. My statistic is not past that, so it is not in the critical region, which means we would fail to reject the null. We don't have evidence of an association between marital status and color of car. So independent would be your null. In this one, we're failing to reject the null. Basically, we're stuck with null. These next few questions are asking us to kind of just find some probabilities based on that table. So this first question is saying the overall proportion of the sample that drove a red car. So total we had 80 out of 150 that drove a red car. And we want 2 decimal places. So 0.53. Would be that one. This one says the value of P parentheses black car. So P parentheses black car just means the overall probability of someone driving a black car. So if there's no line that means given, you'll see what I mean on the next couple, then that just means overall. So overall we have 33 out of the 150. So 0.22 would be that one. And then this one said probability or P parentheses other color car. So again, there's no given line. We're just saying overall. So 37 overall out of 150. Is about 0.25. So then conditional probabilities means we have this given line. So like this first one, P parentheses red given unmarried, means for the unmarried people, what is the probability of driving a red car? So if I'm only looking at the married people, so out of the 86 married people, 45 have a red car. 0.52. And if you remember, our overall proportion of red car was 80 out of 150, which was 0.53. These are really not that different. 53% overall drive red cars, 52% of married people drive red cars. So that proportions are not very different. So P parentheses red given, oh, I did married. So unmarried would be 35 out of 64. So about 55%. So again, overall, we had 53% of people driving red cars, and that works out to about 52% of married people, about 55-ish% of unmarried people. And then we kind of go through the same thing for black unmarried, black married, other unmarried, other married. So just looking at each of those conditionals. So like 22 out of 86 for black given married, 11 out of 64 for black given unmarried, 19 out of 86 for other given married, 18 out of 64 for other given unmarried. So you're going through that same process. And then our last question is basically saying, how do we interpret those conditional probabilities? So kind of what I noticed specifically with the red car, right? We had 53% of people overall driving a red car, 52% of married people have a red car, about 55% of unmarried people have a red car. So in other words, proportions are really not that different. So what that kind of would mean is that those small differences in the conditional probabilities could just be sampling error. This particular sample had a tiny difference between married and unmarried, but it wasn't a significant enough difference for us to believe that overall married people drive different color cars than unmarried people. So those differences were small, so they were probably just due to sampling error. The sample we got just happened to have those small differences. That is your homework 17. If you have any other questions about specific problems, make sure that you let me know.